Okay, we are looking at regions in the complex plane, and our interest is actually to sketch the set as given. The imaginary part of 1 over z is strictly greater than 1, and we want to sketch this set, and we proceed to sketch the set. How do we then sketch the set? Right, so we take note of the fact that at this point, the solution is as follows. We have the imaginary part of 1 over z, which is strictly bigger than 1. We let z be equal to x plus iy, which means, therefore, we shall have the imaginary of 1 over x plus iy, like so, strictly bigger than 1. This means the imaginary part of x plus iy, we multiply it by x minus iy divided by x minus iy, strictly bigger than 1. And this means the imaginary part of x minus iy, we divide it by x squared plus y squared. Like this, n is strictly bigger than 1. Okay, so it is the imaginary part of x minus iy, and we divide it by x squared plus y squared, strictly bigger than 1. Okay, which is the imaginary part of x over, we separate this into the real and imaginary parts, which is x over x squared plus y squared minus iy divided by x squared plus y squared. Like this, and this is strictly bigger than 1. Okay, we want to extract the imaginary part, and obviously one thing we need to understand is this is x over x squared plus y squared plus I into minus y divided by x squared plus y squared, strictly bigger than 1. Okay, what is the imaginary part? Well, the imaginary part of this is minus y over that, which is minus y over x squared plus y squared. And this is strictly bigger than 1. Okay. Well, there's something we realized here at this pointer is that x squared plus y squared is non-negative, but yeah, we avoid division by 0 so that we can be able to write these here. That is if we multiply both sides by x squared plus y squared. And further manipulation reveals that x squared plus y squared plus y, like this, is less than 0. And then now we are here, and we're able to have the following. So we have x squared plus y squared plus 1/2 of y. You square that, 1/2 of the coefficient of y. Okay, yeah, we still have the y. Okay, it's just completing the square from school, so it's nothing new at this level. We still have x squared plus y squared plus y, but we are adding half the coefficient of y on the left, and we are doing the same on the right. And this then is the same as what? Okay, because we want to sketch, because to sketch always, it's easier to convert to x and y. So this is then x squared plus y squared plus y plus 1/2 of 1 squared less than 1/2 of 1 squared. Right, so which means therefore we have x minus 0 squared plus this is 1/2 squared is less than 1/4. So yeah, we can be able to factorize these terms like this. Right. So now this inequality represents, okay, so this inequality represents the region. The region interior to the circle. Right, interior to the circle. The circle that whose interior we're describing, circles have an equal sign here. So that would be y plus 1/2, the square that which equals 1/4. This inequality represents the region interior to the circle, this. Okay, but this circle here has the center. So if we write x minus 0 squared plus y plus 1/2 squared, which equals 1/4, the center is always this one with the negative of that, if there's a plus. Right, for us, or this center can be written in terms of z, and z is x plus iy, x is 0, and I is minus 1/2, which means z is minus I over 2. In radius, okay, the radius becomes the square root of 1/4, which is 1/2. All right, now what do we then get at this point here? Okay, this is what we call the Argand diagram. Right, Argand diagram. Right, and the center is minus I over 2, where here we have real z. Imaginary z. So we have this here. Okay, so we have exactly this. So this is the region we are sort of describing. So this is x minus 0 squared plus y plus 1/2 squared is less than 1/4. Okay. Now, there are things that I want us to discuss as we have sketched this. We shaded the region that is interior to the circle, but also we have made the boundary dashed because this is strictly less than the radius. So yeah, we are describing the region that's interior. But there are certain things I want us to discuss. The idea of what to call the neighborhood. Right, so we're looking at the neighborhood. Right. Right, so I want us to discuss this in detail. Right. An epsilon neighborhood. An epsilon neighborhood. Right. Which is written like this. Of a given point, of a given point, Z0 consists of all points Z lying inside but not on a circle centered at Z0. And with a specified positive radius. Okay, so an epsilon neighborhood, which is written like this, of a given point Z0 consists of all points Z lying inside, okay, but not on a circle centered at, okay, yes, but not on a circle centered at Z0. And with a specified positive radius, epsilon. Okay, we shall just draw this. We shall sketch this one. But now, before we sketch it, I want us to look at what we call a deleted neighborhood. Right, something called the deleted neighborhood. Often we will say, therefore, occasionally, or just on occasion. Right? Occasionally, it is convenient. It is convenient to speak. Okay. Convenient to speak of a deleted neighborhood. Or okay, if we don't want to call it a deleted neighborhood, we call it a punctured disk. Punctured disk. Z minus Z0. Consisting of all points Z in an epsilon neighborhood. in the epsilon neighborhood of Z0, except for the, okay, except for the point Z0 itself. Okay, we shall just sketch these. Okay, the idea of what we call the deleted neighborhood. Occasionally, it is convenient to speak of a deleted neighborhood or punctured disk. Okay, so now we look at the difference between what we call the neighborhood, that is just has the modulus of z minus z0 less than epsilon. And occasionally, it is convenient to speak of a diluted neighborhood or punctured disk, where you have the modulus of z minus z0 greater than 0 less than epsilon, consisting of all points z in an epsilon neighborhood of z0, except for the point z0 itself. Okay, so yeah, we shall discuss that. And so now I want us to discuss these notions very, very carefully. So now we are here, and I want us to look at this. Here is Z0. Okay, and then this one, Z. And then this one, epsilon. Okay, and then now you come here, you have this one, Z minus Z0. Okay, so obviously at this point, we just take an arbitrary point, and we are looking at the fact that the distance between an arbitrary Z0 and Z0, or an arbitrary Z and Z0, okay, we're finding that sort of distance using the modular symbol, and we are able to see therefore that the distance between Z0 here and some Z is strictly less than epsilon, right? And obviously what this describes, this one describes what we call the neighborhood. Describes what we call the neighborhood. Now, the idea of the deleted neighborhood at which now the point Z0 itself is out of the picture. So you can look at things differently. You can look at this. And you have a Z, 0 point. And you have a point Z. And you have the epsilon here, yx, the origin. Obviously, we agree that this one describes the distance between Z and Z0. Okay, and so, okay, just here, just a sec. We agree that this describes the distance between Z and Z0. Okay. We continue. All right. Now, at this point, we are really effectively then saying we are looking at this here. And this is the diluted neighborhood, diluted epsilon neighborhood, or what we call the punctured disk. We're effectively saying the distance between Z and Z0 is strictly greater than 0, meaning that it cannot be 0. So Z cannot be equal to Z0. And therefore we speak of what we call a deleted neighborhood. What do you call a punctured disk. Or you can call it the punctured disk. So yeah, the disk has a little hole there. It's punctured. And I want us to discuss the idea of what we call an interior point. And a point, then we then say a point Z0 is said to be an interior point of a set S whenever there is some neighborhood of Z0 that contains only points of S. It is called an exterior point. Okay, I'm looking at these definitions because they are very important. Exterior point, and shall be using them, but also they are very examinable. So these are the kinds of definitions you'll expect to find in the exam. Right, of S when there exists, right, when there exists a neighborhood of it containing no points of S. Okay, we are saying a point Z0 is said to be an interior point of a set S. Okay. Whenever there is some neighborhood of Z0 that contains only points of S. Okay. So I want us to look at the idea of the interior point and what you call the exterior point. So this point Z0 is said to be an interior point of a set S whenever there is some neighborhood of Z0 that contains only points of S. Okay. Now it is called an exterior point of S whenever there exists a neighborhood of it containing no point of S. Okay, so I want us to look at this carefully. Okay. Here is a point, here is a set. Right, so if one looks at a set S, here is a set S. And we're identifying a point Z0. And I was saying this point is called an interior point whenever you can take a neighborhood. So a neighborhood is like an open set. An open set with the property z minus z0 is less than epsilon. So yeah, this is some epsilon radius. Okay, so as much as we can have some open set, okay, because this is very important, some neighborhood of z0. So obviously, I mean, you take some radius that is reasonable, and this particular neighborhood of z0 contains only points of S. And therefore you can say that z0 is an interior point. From here, this is z0, then we say that z0 is an interior point. But obviously, I mean, you can have an exterior point. How do you characterize an exterior point? So you can have a point there in the plane such that, okay, these things, you can have them in the plane. So, right, so you have so you can have some small neighborhoods. So now here you can have some neighborhood. In other words, you can have some open set like this, such that now this particular neighborhood, according to this here, there is some neighborhood of Z0 that contains only points of S. It is called an exterior point of S. Whenever there is some neighborhood of Z0 that contains, right, yeah, okay. It's an interior point when the neighborhood contains only points of S. It is called an exterior point when there exists a neighborhood of it containing no points of S. Okay, so yeah, no points of S, because S is the yellow thing, and then if you can that point, you can find a neighborhood, an open set around it, such that that open set does not intersect. If you try to find the intersection, it's empty. And therefore, this one is called an exterior point. An exterior point. Like, I'm looking at this because they're very important, but we shall use them. Shall use this. What is a boundary point? What is a boundary point? Now, if Z0 is neither of these, it is a boundary point. It is a boundary point of S. So if it is not an interior point, but it is not an exterior point, then what is it? It is then potentially what we call a boundary point. So it's on the boundary. And let us discuss this a little bit. And let us give a definition. What is a boundary point? What is a boundary point? A boundary point. Right, a boundary point is therefore a point or all of whose neighborhoods contain at least 1 point. 1 point in S, and at least one point not in S. Okay, so yeah. Okay, a boundary point therefore is a a boundary point is therefore a point all of whose neighborhoods contain at least 1 point in S and at least 1 point not in S. So yeah, that one is called a boundary point, and we've given sort of a formal definition. So is therefore a point all of whose neighborhoods, boundary point. So in other words, if you have that this, you have a point Z0, all of whose neighborhoods, well, it's on the boundary, because if you take any neighborhood, the neighborhood is going to have some points that are here and also some points that are here. So it's going to have some points in S and some points that are not in S. So this point Z0 is what we call the boundary point. Obviously, we can see that a boundary point is not an interior point, but it's also not an exterior point. It's just on the boundary of the set S. Okay. Right. Okay, what about these boundary points? If you have a boundary point, another point, another point, another point, that such that there are many of them, but they are on the boundary like this, and they constitute. There are many, but all of them, the points that are on the boundary, but all of them, we look at those points that are on the boundary, but all of them with no exception. And we give a formal description of those. In other words, we continue to then say the totality, right? The totality of all boundary points is called the boundary of S. We continue to say the circle, this one. Well, this is the same as x squared plus y squared equals 1. Circle centered at the origin of unit radius. For instance, is the boundary of each of the sets. Okay, this circle is the boundary of each of the sets if you consider the interior here, and here you consider, okay, here this will be the interior, but this is going to be the interior plus the boundary. So the totality of all boundary points is called the boundary of S. We have defined the boundary of a set. What is the boundary of a set S? The boundary of a set S is the totality of all boundary points of the set S. The totality of all boundary points of the set S constitutes what we call the boundary of S. So in other words, if we consider all these boundary points, but all of them, they form the boundary of the set S. Okay, so it's something you need to take note of there. The circle mod Z equals 1, which is the same as x squared plus y squared equals 1, for instance, is the boundary of each of the sets less than 1 and less or equal to 1. A set, right, is open if it does not contain any of its boundary points. A set is open if it does not contain any of its boundary points. Okay, and this is very important. Right? Points here. So a set is open. Okay, we are defining an open set. What is an open set? So a set is open if it does not contain any of its boundary points. Okay, so what is an open set? It's basically any set that does not contain any of its boundary points. That set is said to be open. And also you can say this. A set is open. Is open if and only if its points, if and only if each, I want to say if and only if each of its points, if and only if each of its points is an interior point. Is an interior point. A set is open if and only if each of its points is an interior point. A set is open if and only if each of its points is an interior point. So in other words, if you find a neighborhood like we saw of any of the points in S, that neighborhood will always contain points in S. Points in S. Okay, so yeah, just take note of that. Okay, now the set is closed. The set is closed. What is a closed set? We are looking at the closed sets because they will ask you this in the exam. Right, a set is closed if it contains all of its boundary points. Okay, this is a very nice definition. boundary points. And the closure. And the closure of a set S is the closed set consisting of all points in S together with the boundary of S. Okay, so a set is closed if it contains all of its boundary points, and the closure of a set S. Okay, now I want us to look at this one. A set is closed. When is a set closed? It is closed if it contains all of its boundary points. And the closure of a set S is the closed set. Okay, the closure, we're defining the closure. What is the closure of a set? Right, the closure of a set S is the closed set consisting of all points in S together with the boundary of S. That is the closure. If you take all the points in S together with the boundary of S, that constitutes the closure of S. Okay, so we shall discuss the notion of the closure. Okay. And this goes without saying that there's some sets that are neither open nor closed. Some sets. Some sets are, of course, neither open nor closed. Neither open nor closed. Okay. On that note now, okay, an example. Observe that the punctured disk, we have the pleasure of seeing what you call an example of what you call a punctured disk. The punctured disk is neither open nor closed. Okay, it's neither open nor closed. So this punctured disk is neither open nor closed. I mean, how do we sketch it? So we take a unit circle, but now that is such that it doesn't have the center, doesn't contain the center, and it's a radius 1. So if you take, but obviously this, okay, let me just say write down so that you can understand what we're talking about. Because if you let z be x plus iy, then this is the modulus of x plus iy like this. So this is the same as this. But now the modulus by definition is the square root of x squared plus y squared, less or equal to 1. Okay, you square both sides, which means x squared plus y squared is less or equal to 1. Okay, now this one we can sketch using metric knowledge. What kind of a sketch is this? Okay, this, okay, it looks like something we call an annulus. But it is not. It is not an annulus. Right, so it's, yeah, it's sort of an annulus because anyhow, you remove the origin, and then now you take a circle of the region like this. Okay, so the radius, the distance from here to here is 1 unit. Okay, but we are speaking about we're shading the region that is interior here. Okay, and therefore this is y and that is x. So this is what we have. And this is the punctured disk. Why is it punctured? It is like a disk because it is like this, and it has a little hole in the middle. The hole, why is that the hole? Because any sum of the squares of the points x and y here will actually be greater than 0, so that it cannot be 0. So in other words, 0 is out. Okay, so 0 is out of the picture. So it means x and y cannot both be 0, but you can allow x alone to be 0 so that y is bigger than 0, and so on. So what are we trying to say here? We, as we're saying here, that the punctured disk is neither open nor closed. This one is neither open nor closed. Okay, so this is very, very important for us. Okay, I want to be very accurate in the way I describe it. Strictly speaking, then, the region around 0 is sort of obviously an open region. It's sort of an open region around the origin. But here it is solid. The boundary is solid because it can be equal to 1. But here it's like broken around the origin. Broken because it's not equal. It's not equal. Yeah. But I mean, with this notion, then mentioning the fact that it can be written in many ways, and there's times when we're gonna obviously include that, and I'm gonna discuss a couple of things that are very, very important on this. But yeah, that is what, just an example of a punctured disk, and we shall have other more discussions, okay, following this one. Okay. Okay, now let's look at this one. Another example. The set. The set C of all complex numbers. Okay, so if we look at the set C of all complex numbers, is on the other hand, both open and closed. Okay, very important. Both open and closed, since it has no boundary points. It has no boundary points. Okay. The set C of all complex numbers. Complex numbers means that it contains all z that are x plus iy, such that the x and the y are real, but I, by definition, is the square root of -1. Okay, this set of all complex numbers is, on the other hand, both open and closed. Okay, very important. It is both open and closed. Since it has no boundary points, it has no boundary points. Okay. It has no boundary points, so it's both open and closed. Okay, think about this. Think about the description there. But now, what is a connected set? An open set. Right, an open set. S is connected. Is connected if each pair of points Z1 and Z2 in it can be joined by a polygonal line consisting of a finite number of line segments. Okay, a finite number of line segments joined end to end. That lies excuse me. All right, that lies entirely in S. An open set is connected if each pair of points Z1 and Z2 in it can be joined by a polygonal line consisting of a finite number of line segments joined end to end that lies entirely in S. Okay, so yeah, we shall look at an example of this. So, what are we describing here? We're describing what we call a set that is connected, and the notion of what we call a polygonal line comes to the surface. But an open set S is connected if each pair of points Z1 and Z2 in it can be joined by a polygonal line consisting of a finite number of line segments joined end to end that lies entirely in S. Then that set is said to be connected. And we shall be looking at connected sets here and domains and so on. Okay, now let us look at some examples before I even delve into the connected sets in more detail, etc. Okay, let's get into some examples. The open set. The open set, this one, modulus of Z is less than 1, is connected. is connected. Okay, so because it satisfies the definition of an open set, because if you take any polygonal line, if any polygonal line will actually that contains points that actually joins the points in S will actually be entirely contained in S. Okay, so also the annulus, something called an annulus. This one is special quite to this course because we shall be looking at theorems, Rochet's theorems, and so on when we do contour integration, and the notion of an annulus become very important. So the annulus, this one, is of course open, and it is also, well, this is called an annulus. Okay, you shall look at that. So annulus means that you have two radii, and it's like you have two concentric circles. We shall discuss. We shall just sketch this one. So in other words, the annulus, this is of course open, and it is also connected. Okay, it is also connected. So in other words, if you are to look at this sketch here, we shall look at some circle of radius 1, and then another circle of radius 2, like this. So yeah, 1, 2, and then now we can then take some points. Let us consider some points, like I can take some points Z1 here, another point Z2, and then now you can have, you can join them. You can join them like that. The open set is connected. The annulus is of course open. We have discussed an open set. Right, so but now the annulus is of course open, and it's also connected because if you take some points, then you can take a polygonal line, and this polygonal line that joins the points is entirely contained in S. Okay, if we are to just look at this annulus as set S, then this is the annulus. So this annulus obviously says the modulus of Z is strictly bigger than 1, but less than 2. So we are actually describing the region that is a what? Like a donut. So we are discussing this here. Like that. We're discussing that. So yeah, it's that kind of a description, but we've put it here in the Argand diagram. Like that. Okay, I want us to look at other things like domains. Let us discuss domains. What is the domain in complex analysis? Okay, now somebody can say domain is a set of pre-images. It's a set of pre-images, but now at this point, we're looking at a domain in complex analysis. A non-empty open set that is connected is called a domain. A non-empty open set that is connected is called a domain. So what is just defining a domain here? Two things. Okay, it must be non-empty. It must be an open set, but it must also be connected. Then you have a domain. Okay, right. Now, and then now, what about what is a region? What is a region? Okay, I want us to include a note. Note that any neighborhood is a domain. A domain together together with some none or all of its boundary points is usually referred to as a region. Note that any neighborhood is a domain. Okay, so this is very important. We define the neighborhood. So any neighborhood is a what? Is a domain. A domain together with some or none or all of its boundary points is usually referred to as a region. Okay, this is very important. So if you look at the region, a region can have potentially some, or it might have nothing, like nothing. That refers to the boundary points. In other words, a region can either have a boundary or no boundary. So that still qualifies to be called a region. What is a bounded set? What is a bounded set? Okay, we defined the boundary, but let us have a clear description of a bounded set. A set S is bounded if every is bounded if every point in S lies inside some circle modulus of Z equals R. Otherwise, it is unbounded. It is unbounded. It is unbounded. Right, so a set S is bounded if every point in S lies inside some circle mod of Z equals R. Right, otherwise it is unbounded. Both of the sets both of the sets 3 and by 3 we mean this one Okay, let me write here. Right, both of the sets 3, and by 3 we mean modulus of z is less than 1, and modulus of z is strictly greater than 1. Are bounded. Okay, both sets are bounded regions. Okay, so both sets, these sets are bounded regions. Okay, these are bounded regions. So yeah, the region can always, as said, already have a boundary or no boundary at all. And so these two are bounded regions, and the half plane real z is unbounded. Okay, and the half plane real part greater or equal to 0 is unbounded. Okay, let's look at the half plane a little bit. Just sketch it. And right, obviously the half plane itself, imaginary z, and this one is real z. So if we are to look at real z is greater or equal to 0, so we are looking at the part that is real part greater or equal to 0. And obviously, because this one goes on and on to infinity, it is unbounded. Okay, why are we even speaking about the unboundedness of this? Okay, this is unbounded. Why? Why are we talking about the unboundedness of this? Okay, we are speaking about bounded sets. We said a set is bounded if every point in S lies inside some circle. Otherwise, it is unbounded. Okay, so we have some circle, and it is unbounded. If it goes outside the circle and keeps going up and up and up, it is therefore unbounded. Okay, now I want us to look at specific examples here that are very, very important to us. And let us discuss the following examples. Right, so these following examples are very, very important to us. So we looked at this, but yeah, we have a chance to spend a bit more time on it. Sketch. Sketch the following. The following sets, and determine which are domains A, z minus 2 plus I less or equal to 1. You have 2z plus 3, which is bigger than 4. C, imaginary z is bigger than 1. D, the imaginary z equals 1. E, 0 is less or equal to the argument function of z is less or equal to a quarter pi. Z is not 0, always for the argument we take Z not 0. Okay, here modulus of this is greater or equal to modulus of Z. Okay, so now we sketch the following sense to determine which are domains. Okay, so but now and also we're going to proceed to say which sets are neither open nor closed. Neither open nor closed. And which sets are bounded. So now let's look at the solutions to this. Let's look at the solutions to this. Right, so we shall look first at this one, A. Okay, so A is Z minus 2 plus I less or equal to 1. X plus IY minus 2 plus I less or equal to 1, which is X plus IY minus 2 plus I less or equal to 1. X minus 2 plus I, 1 plus 1 less or equal to 1. And then you have here X minus 2 y plus 1 squared is less or equal to 1. X minus 2 squared y plus 1 squared, you square both sides, you get this. So, and once you get this, once you get X minus 2 squared plus y plus 1 is equal to 1, the center that is involved is 2 minus 1, or you can say X is what? Because it's always X plus IY, and then X is this one. So X is 2 and minus I. Okay, so in other words, you have this here, X, Y. Okay, now when X is 2 and Y is minus 1, and then the radius is 1, see? Okay. X is 2, and then you have minus 1. And then you are saying that the radius is 1, so it's going to touch, but it's not going to touch the, because now here the distance from here to here is 2, but this is less or equal to, so it includes the boundary, etc. So you'd have this. Right, so obviously, I mean, there are a couple of questions we need to answer about this. All right. So is it closed to, so it is closed? Right, it is closed. It is closed and bounded. It is closed and bounded. So this one is closed and bounded. Right. And then now we look at the next one, B. Okay, is it a domain or not? Okay, let's answer that part. So this set is not a domain. Right, it is not a domain. Since it is not open. It is not open. Okay, not a domain since it is not open. Okay. Want to mention something. So here we define a bounded set. A set is bounded if every point in S lies inside some circle, otherwise it is unbounded. So yeah, we had an opportunity of the, so in other words, that set there, we've already seen that it is bounded. Why is it bounded? Because every point in the set lies inside some circle. Okay, that one obviously is some circle there. And now we also have had a chance to discuss the notion of a closed set. What is a closed set? A set is closed if it contains all of its boundary points, and the closure of a set S is the closed set consisting of all points in S together with the boundary of S. Yeah, so that set there is both closed and bounded, but it is not a domain because domains are open and connected sets. And surely this set here, it is not open. Right, then we defined an open set. And to recap very quickly, in our description of an open set, we said an open set, right, is connected if each pair, okay, so it's fine, but that did not, right, a set is open if it does not contain any of its boundary points. In real analysis 3711, MAT 3711, we say the set is open if its complement is closed. The set is open if its complement is closed. Okay, that's one description or categorization of open sets. To know if a set is open, you take its complement, and if the complement is closed, then you know the set is open. Okay, obviously here in this course, we're saying, because this is complex analysis versus real analysis, and they're trying to teach the same thing, but yeah, complex and real spaces differently. So a set is open if it does not contain any of its boundary points. Okay. Right, let's continue now and look at more things here. And I want us to look at part B, which is 2z plus 3 is greater than 4. Okay, at this point, you let z be x plus iy. Okay, we just want to draw the graph of this. Okay, we can do it differently. I mean, in mathematics in general, we use the fact that z minus a equals r is the circle of center A and radius r. And now we can use this fact to then say this point, the coefficient of z must be 1, and it is 2 here. So we can factor out 2. I mean, there are many ways to look at these. We might not need to, we can do x and y so that it looks like in school. But now this one is the modulus of 2, the modulus of z plus 3 over 2, bigger than 4, 2 here. Z plus 3 over 2 is bigger than, if you divide 4 by 2, you get 2. So you can see this one can be written as z minus int minus 3 over 2 is bigger than 2. Okay, so in the center is minus 3 over 2, and then we are looking at the region outside this circle of radius 2. And then obviously, I mean, this can also be seen using our high school things. high school tools. And high school tools are X plus IY, the things we learned first at grade 12. So you have this one plus 3. And then now this one is bigger than 4, which is 2x plus 2iy plus 3 is bigger than 4, which means that it is 2x plus 3 plus I 2y is bigger than 4. Okay, so take a look at these now and think very carefully about it. But now this square root that we're looking at here is the modulus of this is 2x plus 3, and then you square this, and then you have 2y, and you square this, which is bigger than 4. So in other words, you have the square root of 2x plus 3 squared plus. And then you have 2y is bigger than 4. Okay? And okay, let's see now what we've done here. Yeah, that's okay. Because the modulus is the square root, bigger than 4. You square both sides, which means 2x plus 3. You square these, that's like 4y squared. Okay, yeah. It's bigger than 4. Factor out the 2 here. Factor out the 2 and you square it. It becomes 4, and this is x plus 3 over 2. You square this, which is 4y squared greater than 4. Divide through by 4, so that the coefficient of the perfect squares, the coefficients themselves are 1, and this is true because divide by 4, and it's the sort. Okay, excuse me. Okay, here you squared both sides, and so this was supposed to be 16, because if you square like this, like that, you have a 16 here. Okay, so that you divide 16 by 4, this one becomes a 4. Okay, so in other words, obviously, we're looking at the fact that this is x plus 3 over 2 squared plus y squared, and it is bigger than 4. Or you can see z plus 3 over 2 is bigger than 4. We saw it here. Okay. It's bigger than 2, excuse. Yeah. It's bigger than 2 here. Bigger than 2 here. We divided 4 by 2, so it's bigger than 2. Certainly bigger than 2, so yeah. We're just checking that one. So it's bigger than 2. Okay, obviously it's the same thing because this one is x. How do we see the radius of a circle? So it's always x squared, y squared, and this is like r squared, which is 2 squared. Okay, so obviously this is the same thing. In the complex analysis context, we discuss circles like this. Well, it's a region. A region can either have a boundary or no boundary. I mean, that we just saw now. We call it a region in the two-dimensional plane, the Argand diagram. So in which case, therefore, okay, we need to just sketch this one. So how do we sketch this? Let us look at the sketch together. So if you have x plus 3 over 2, we right. Okay, just yeah, we're continuing now to look at these things here. And okay, so looking at these now, what do we get out of this? We get a couple of things. Okay, we're continuing just now, and I want us to look at more things that remain very, very important to us. Right. So right. So we're going on. Okay, yeah. So we're looking at that one. Okay. So we continue. All right. So right. So in other words, now we continue to analyze this now. Okay, I was looking at this one, and right. So in other words, we have this. Okay, yeah. I was saying we need to sketch these things. So this one is plus y squared, and this is bigger than 2 squared. And this one here is the modulus of z plus 3 over 2 is bigger than 2. Okay, now right, so right, so in the end then we are trying to analyze what is happening here. Okay, the couple of things that are very important. So we are trying to look at the sketch and what is the center? Right, so the center will be minus 3 over 2, 0. Right, so the center will be minus 3 over 2, 0. So yeah, even here you can see the center is going to be like, because normally to see we need to put a minus because of the fact that the formula is z minus a bigger than 2. Okay, so right, so if it's z minus a is bigger than 2, so obviously at this point, if this is minus 3 over 2 for the x, right, and 0, and now we are looking at the fact that the radius is 2 units, r squared here. So r is 2. So if the radius is 2 units, okay, this is the distance from here to here is like 1.5. So you need another 0.5 to make 2 units. Okay, so obviously now we are going to look at the boundary like this. And then now, obviously, we're looking at the region that is greater. Okay, this thing must be like a circle, please, but it looks oval, I understand that. So, but then this is the region. Because it's greater, so we're looking at things outside, but the boundary is also not included. Okay, so this one of us is described by this particular circle, 3 over 2 bigger than 2. Right. Now, the couple of things that are very important, like this other one, imagine z bigger than 1 in C. Okay, let us sketch this one. Did I mention that? Yeah, in C. Just practicing some of these here. Some of these I'm going to leave as home activity. Or yeah, I said imagine z. Okay, yeah, but now there are a couple of things. Like obviously, you can see that B is open. It is open. And so because it is open, then it is called a domain. This one is a domain. Because domains are open and connected sets. So it is open. And how is it connected? its connected nature is seen by a polygon. You can draw a polygon Z1, Z2, so that in the end, then you have Z1, Z2. Now these points will actually be, this polygonal line will be entirely contained in the set. If you had to call this set the set S. Okay, yeah, something very important. Let's look at the part C. Now in this one here, we let Z to be X plus IY, which means that you have the imaginary, which is X plus IY bigger than 1. Okay, we're looking at the imaginary part, and the imaginary part of this is the Y. So you only take the Y. So this is the same as this. But how do you draw the graph of these here is very, very straightforward. So we're looking at this here. Y equals 1. Y equals 1. Greater than 1. Okay, so this is what we get. This set here is a domain. Okay, this set here qualifies to be called a domain. Okay, so in other words, this set here is open and connected. It is open and connected, and hence a domain. It's open and connected, and hence a domain. But we agree that this set goes on and on and on towards like plus infinity. So this set is unbounded. It is unbounded. Okay, now there are other things that we can look at, like your okay, this D part is very straightforward. Let's just look at D. And then we shall look at a little bit subtle notions. Okay, this one we shall be very fast with it because it's very straightforward. If Z is X plus IY, we've already seen the inequality part of it, but we shall see X plus IY equals 1. Okay, the imaginary is Y equals 1. So, okay, so yeah, if Y equals 1, let us draw the graph of this. So that would be imaginary Z, real Z. So obviously at this point, this is going to be equals 1. Yeah, like this. It is closed and not open, and hence, okay, this one, it is closed. It is closed, not open, and hence not a domain. Okay. It is closed, not open. Okay. And hence not a domain. Moreover, this set is not bounded. It is not bounded. Right, it is not bounded. Okay, because it goes either in both directions, towards minus infinity, but also towards plus infinity. Okay, let's look at part E. Okay, here is part E. Let's look at the argument. Very interesting. So now the argument of Z, which is the principal argument with capital A, which is a 0 less or equal to the argument of Z. Okay, strictly speaking, it must be small letter. See what I used here. Okay, because yeah, we shall discuss principal and non-principal arguments. So argument Z, ARGZ, but small letter, meaning we can take any angle. We're not specific to a restriction. So we're going to look at 0 less or equal to the argument of Z. Less or equal to pi over 4. We must draw the graph of this. We must sketch the set. But we sketch this set when Z is not 0. So in the end, okay, Z is not 0, meaning that we're going to put an open circle here like this. And then this is like pi over 4 here. And we shade here like this because we take all those angles that are between 0 and pi over 4. Okay, so that is sort of the sketch. It is not open, and hence not a domain. Not a domain. We're saying this set is not a domain because it is not open. I want to say more. It is also not closed. Not closed since the boundary points or the boundary point since the boundary point 0 does not belong to the set. It does not belong to the set. All right, it is not bounded. It is not bounded. It is not closed since the boundary point 0 does not belong to the set. So it is not closed. Okay, because this point does not belong to the set. Okay, because 0 does not belong to the set. Yeah, so it is not a bounded set, but this is the sketch of it, and this is y and that is x. Okay, now I want us to look at another one. Let us look at the part F before we look at the closure of sets. So part F is z minus 4 is greater or equal to modulus of z. let Z. So okay, now you have this here. Okay, so you have this here. You square both sides, F. Okay, so if you square both sides, it then means therefore that you have x minus 4 plus y squared. And we have greater equal to x squared plus y squared. And so what is this? Let us analyze this together. Okay, if we square this one, we get x squared minus 8x plus 16 plus y squared is greater equal to x squared plus y squared. And x squared cancels, y squared cancels, leaving us with minus 8x plus 16, and this is greater equal to 0. Okay, this is minus 8x is greater equal to minus 16. Divide by 8, which means it's less or equal to 2. So what kind of a set is this? Okay, so in other words, part F, we are describing the set Z minus 4 greater equal to mod Z. Okay, so now we have the description. This one is real Z. This one is imaginary Z. And therefore, you take an arbitrary point, the distance here, and the distance here. Okay, so see this one. So 0, 4. Okay, midway is 2. Okay, because it's less than or equal to 2, so you're going to have solid line like this. But it's going to be looking at we are looking at this region to the left. Modulus Z, Z minus 4, 2. Is this one here? Good. This is Y and this is X. Okay, what is the story about this? Well, the story about this is that we are describing this set here, like this. Also describing this here. So you are effectively then saying the modulus of Z is actually smaller than the modulus of Z minus 4, so that the modulus of Z minus 4 is sort of above. So if this is above, the modulus of Z minus 4 is smaller. Okay, so it's sort of what is being described. But in other words, this set can be written in this form. Right? And now I want us to describe this set. So if you're looking at z minus 4 greater or equal to mod z. Oh, goodness me. Okay, we continue, please. This set consists of all points z such that the distance between z and 4 is greater than or equal to the distance between z and the origin. This set consists of all points z such that the distance between z and 4, okay, distance between z and 4 is shown by the modulus, is greater than or equal to the distance between z and the origin. Z and the origin means distance between z and 4 is greater than or equal to the distance between z and the origin. Okay. Moreover, we look at the fact that if one describes this set here, this set is closed, but not open, and so not a domain. Okay, we're to tell if it's a domain or not. It is not a domain because it is closed. It is not bounded. It is not bounded. Okay. Now I want us to focus on the closure. Sketch the closure of the set A minus pi argument of z less than pi. And then B, the modulus of the real part of z, the modulus of the real part of z is less than the modulus of z. C, the real part of 1 over z is less or equal to 1/2. D, the real part of z squared is strictly bigger than 0. But yeah, let us sketch the closure of the set in each case. Let's look at the first one, the argument. Right, so part A focuses on minus pi less than the argument of z less than pi, but we are looking at z not 0 as usual for the argument. Let us draw the closure. We want to sketch, before we're sketching the sets, but now we are sketching the closure. So we note that the closure of the set argument of z is the entire plane so the closure of the set, this one is the entire plane. The closure of the set, that is the entire plane. XY. And the closure. Okay, so if you consider the closure, you consider the boundary. So you can see that this 0 was not there, but now in the closure we shall include the 0. And therefore it is the entire plane. So yeah, the closure of the set, this one here, is the entire plane. Right, it is most certainly the entire plane. Just one more, part B, and then she'll give you homework. So now here, if you look at the modulus of real z is less than modulus of z. So if you let z to be x plus iy, so that you have the real z. So we continue.
Charging per assignment.
We continue. Let z to be x plus iy. So that now you'd have the modulus of the real part of the x plus iy, which is less than, okay, we're interested in just sketching the closure. The real part of this, right, what is the real part of that? So at this point, we're able to see that the real part of this number is x, but now it is within the modulus symbol. And then here the length or the modulus of the x plus iy is x squared plus y squared. Okay, we saw that because now we know that z equals x plus iy means the modulus is the square root of x squared plus y squared. Okay, so yeah, part B, we are finishing. The modulus of x is strictly less than the square root of x squared plus y squared. And then now you need to square both sides so that x squared is less than this. And what is this the same as? So at this pointer, you can see that x squared cancels x squared, so that you have y squared is bigger than 0. Okay, y squared bigger than 0 means the modulus of y is bigger than 0. Okay. Like that. And that means, therefore, hence, the closure Hence the closure of the set modulus this one is less than modulus of Z is the entire plane. Right, the closure of the set is the entire plane. You're right. Is the entire plane, excuse me. Okay, I want us to analyze why is it the entire plane. Okay, because obviously we can see that this describes, if you say the modulus is bigger than 0 of y, y squared is greater than 0, the square of a real number is greater than 0, well, it would mean that the modulus of y is bigger than 0, and that would mean, therefore, this one does not include y equal to 0, but the closure will include all that, so that in the end, then if this one is y and that is x, so the closure will be such that it will actually contain everything else. So you'd have that this should be the closure, right? So this should be the closure, and so all right, this will be the what? The closure. All right, so yeah, excited. Okay, I think that this is very much enough because we just supposed to sketch the closure. So this is pretty much sufficient for today. And so, see, there are many things I can say here. For example, I mean, in the part B, this is very, very interesting because in part B, you're saying y squared is bigger than 0. I mean, it is true that for any real number, the square is bigger than 0 for any real number. But this can also be seen like this. You're multiplying two numbers and you're getting 0. What can you say about y? Well, it means that if multiplying two numbers, so these are two numbers, it means y is greater than 0, y is greater than 0, or y is less than 0, y is less than 0. Because if it's negative, negative, then you have that. Okay. So if y is negative, you multiply it by negative both sides, you have what? You multiply by -1, y. By -1, you multiply the 0. The inequality changes direction so that you have minus y is greater than 0. Okay, so you have these two instances, but they together mean the modulus is bigger than 0. And therefore, now you sketch these. You sketch y greater than 0. Where is y greater than 0? So, I mean, obviously now we're looking at the closure of this and the closure of this. This was not including y equal to 0. It was saying y is greater than 0, but the closure includes 0. So yeah, in the end, then you have the entire plane for that part B. And so now, please, as homework, you have the following things to do. You have this one to do and that one to do. Okay. Okay. We continue. Okay, yeah, we'll continue. Right, I think that it's enough for today. Thank you so much for joining us. So yeah, you shall try C&D, then I'm gonna see you tomorrow at 4 p.m. Okay, yeah.
Can we end the recording?
Okay, that's fine, thanks. Let me see.